Hello everyone, this is Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. Today we are going to discuss about inverse filtering in image restoration and segmentation. Okay, in image restoration techniques, we have to consider the inverse of a degradation process. Depending on the knowledge of degradation, it can be classified into deterministic, random, linear and non-linear. In deterministic, if prior knowledge about degradation is known. Random if not known. Linear, restore the image by a filter. Example, inverse filtering. Here the drawback is ringing artifacts near edges. And in non-linear function is used and ringing artifacts are reduced. Okay, see here, image restoration model. Your input is f of xy, which is fed into degradation h of xy. It is added up with e2 of xy, and the output is g of xy is fed with restoration filters, and finally we'll get f dash of xy. In this model, f of xy is input image, h of xy is degradation, f dash of xy is restored image, e2 of xy is additive noise, g of xy is degraded image. Okay, in spatial domain, g of xy is equal to f of xy convolution with h of xy. In frequency domain, g of kl is equal to f of kl, which is dot product with h of kl, where g, f and h are Fourier transform of g, f and h. See here, in linear restoration technique, these techniques are very quick and simple but limited capabilities. It includes inverse filter, pseudo-inverse filter, Wiener filter, constrained least square filter. Okay, in inverse filtering, if we know exact PSF and ignore noise effect, this approach can be used. What do you mean by this PSF? What is PSF? PSF is point spread function. It is actually, this PSF is used to visualize the point spreading in the image. In practice, PSF is unknown and the degradation is affected by noise, and hence this approach is not perfect at all. The only one advantage is this is very simple. See here, from image restoration model, we can write G equal to HF plus eta. Then the error function becomes eta equal to G minus HF. If we wish to ignore eta and use f cap to approximate under least square sense, then the error function is given as j of f cap, which is equal to modulus, double modulus g minus h f cap square. It is equal to g square plus h square f cap square minus 2g h cap. Okay. To find the minimum of g of f cap, the above equation is differentiated with respect to f cap and equating it to 0. Solving for f cap, we get f cap, it is equal to ht inverse multiplied with htg, it is equal to h inverse g. And taking this Fourier transform on both sides, we will get f cap of kl, it is equal to g of kl by h of kl. The restored image in spatial domain is obtained by taking inverse Fourier transform of the previous formula. See here the inverse filtering effect. See the original image and the degraded image and the restored image, which is exactly same like original image. Okay, while coming into inverse filtering with noise, we have some advantages while using inverse filtering. Here the advantages are, it requires only blur PSF and it gives perfect reconstruction in the absence of noise. The drawbacks are, it is not always possible to obtain an inverse singular matrices. If noise is present, inverse filter amplifies the noise. Better option is Wiener filter here. And see here the examples of inverse filtering with noise: original image, degraded plus noise image and a restored image. And pseudo inverse filtering, for an inverse filter, f cap of kl, it is equal to g of kl by h of kl. Here h of kl represents the spectrum of PSF. The division of h of KL, it leads to large amplification at high frequencies and thus noise dominates over image. To avoid this problem, the pseudo-inverse filter is defined as 1 by h is equal to 1 by h if h greater than epsilon. If h less than or equal to epsilon. The value of epsilon, it affects the restored image. With no clear objective selection of epsilon, the restored images are generally noisy and not suitable for further analysis. See here the examples of pseudo-inverse filtering: original image and degraded with noise image. See here, pseudo-inverse filtering with epsilon equal to 0.2. Pseudo-inverse filtering example with epsilon equal to 0.02. See here, epsilon equal to 0. See, pseudo-inverse filtering with epsilon equal to 0 output. So here we use SVD approach for pseudo-inverse filtering. Here the advantages are effective with noise amplification problem, as we can interactively terminate the restoration. It is computationally efficient if noise is space variant. Here the disadvantages are presence of noise can lead to numerical instability. So we use single value decomposition technique here. Thank you.